what is the value of ampersand y after the code on the left executes? So we've got x set to 50, y is a pointer to an integer. Okay, well, in this case, it's just going to be 100 because we're explicitly setting it to 100 on the last line of the code. So that one was pretty easy. Now this question is a little trickier. It says, what is the value of x after the code on the left executes? Well, x is set to 50, y is a pointer to x, and then we dereference y and set it equal to 100. So that's actually also going to be 100 because we're setting x through y, which is a pointer to x. I mentioned earlier that pointers can be dangerous, and that is definitely the case. If a pointer points to nothing, then its zero value is nil, right? So this is the same for interfaces or errors, right? In Go, fairly often you'll be checking at runtime if a value is nil or not. And the thing about pointers is, if you ever try to dereference a pointer that doesn't point to anything, your code will panic. So pretty much any time you dereference something, you should be checking before you dereference it to make sure that the pointer actually points to a valid location in memory. So this assignment says, let's make our profanity checker safe. Update the remove profanity function. If the message is nil, return early to avoid a panic. Okay, so let me run it in its current state. And you'll see we get this nasty panic here. It says invalid memory address or nil. Okay, so what we need to do here is if message equals nil, return nothing, right? If we've been given an invalid input, we'll just bail early. Another way to do this, if the assignment expected something different, we could return an error here, right? We might do something like return errors.new invalid input. I think that would also be a good way to write this function. But we've been asked to just do a naked return, so we will do that. Let's submit it. So let's talk about how pointers are used in conjunction with methods. So you'll very frequently see that methods actually take a pointer receiver rather than a non-pointer receiver. And typically that's done because the method will be making changes to the instance of the type itself, in this case, a struct, right? So we have this car with a color field, and the set color method on the car is going to change the color, right? And so here, if we create a new car, we set the color to blue and then print it, you can see it's been updated to blue instead of white. Now, contrast that with a non-pointer receiver. This acts like a normal function, right? We don't have a pointer, so we don't have a reference to the location in memory. So if we update the car's color to blue, it actually just stays white. It doesn't persist that change. So that's why I say that it's more common that you'll see pointer receivers on methods than non-pointer receivers, but you will definitely see both. So the question is, which is more widely used in Go? And the answer is pointer receivers. Now, when it comes to pointer receivers, one thing that's important to understand from like a syntactic point of view is that even though the input on the left-hand side, right, the receiver is a pointer, when you actually call the method, you can call, in this case, right, the grow method, you can actually call it on just a normal value or a pointer. It will sort of cast the value under the hood to a pointer if it isn't one already, right? So C, in this case, is just a circle. It's not a pointer to a circle. But when we call c.grow, the pointer to the circle is passed into the method. So we didn't need to kind of explicitly, cast C to a pointer to a circle by, adding an ampersand right here. Okay, so with that understood, let's move on to the assignment. So the assignment says, fix the bug in the codes that set message sets the message field of the given email structure, and the new value persists outside the scope of the set message method. Okay, so we've got this email struct, we've got the set message method. If I run the code in its current state, we've got before message, this is my first draft, Sandra, Bullock, after looks identical, right? And if we go and take a look at the test suite, then we can see that set message is being called. This is my second draft. So we would have expected this message to say, this is my second draft instead of this is my first draft. The reason it's not happening is because this function essentially doesn't do anything. This method does nothing because this is not a pointer to an email. Let's go ahead and run that again. First draft, second draft. Perfect. Let's submit that. Everything we've done up to this point in the course has been in the browser. We've been writing code right in our text editor on boot dev. Now we're going to break out of that environment and do some local development on our own machine. We're going to figure out how to use the Go toolchain to build real production Go programs. But before we do that, let's talk a little bit about packages. We need to understand packages in order to build our own Go programs. Now, you've probably noticed that up until this point in the course, every coding assignment has had the words package main at the top of the file. That just means that we've been writing code within the main package. And that's actually really important. The main package is a special type of package. It's a package that runs as a standalone program. So anytime you're writing an actual application that you need to run, say on the command line or as a server, you'll be writing code within the main package. A package with any other name, so any name besides main, is a library package. And basically what that means is it's imported by other libraries and application code. So oftentimes it's just imported by a main package so that it can use it. If you're familiar with NPM from JavaScript or pip from Python, that's effectively what a non-main package is in Go. It's just some code that you can publish as kind of a standalone library that then other developers can use in their main packages, in their actual applications. So let's take a look at an example here. So you're probably familiar with this style of code. It's what we've been writing all throughout this course. We've been writing within the main package because we've been writing executable scripts, right? Code that actually runs and does something. And then we have this import statement where we've typically just been importing from the standard library, but the standard library is made up of library packages, right? Like the FMT package or the math/random package. The interesting thing about the main package is that it always has a main function, and that main function serves as the entry point to the program. So packages that are not main packages, they're library packages, will just export functions, named functions, to be used again by other libraries and application code. Only main packages will have a main function that runs when the program starts. So to jump into the coding assignment, it just says fix the bug in the code. So let's go ahead and run the code and see what happens. Nothing happens, right? We're stuck in this infinite loop. Apparently this code compiles and then does nothing. It's kind of a weird behavior, right? In order to fix this, all we need to do is update this to be a main package so that we get as output for our code a runnable executable, a script that we can actually execute in the browser. So let's go ahead and run that. And we get starting Mailio server, stopping Mailio server, kind of as we would expect based on this code here. So I'm going to go ahead and submit that. So we're familiar with main packages, but what about library packages? Well, by convention, a package's name is the same as the last element of its import path. So for example, the math/rand or math/rand package from the Go standard library has files that begin with package rand. So the rand package lives at math/rand. Now, it's important to point out that the standard library actually has another rand package at crypto/rand. So they're both kind of the rand package, but they have different import paths. When a package isn't part of the standard library, when, for example, you make your own library package, the import path is typically the same as the remote URL that you'd use to go look at that library's source code. So, for example, in our fictitious Mailio products, right, part of the Textio conglomerate of messaging products, they might have their own GitHub namespace. It's /Mailio. So github.com/Mailio is their GitHub organization. And then maybe they create their own package or their own repository on GitHub called Rand, and that's where the repository for their Rand package lives. That's where the source code lives on the internet, right? github.com/malio/rand. Now, that package's name, by convention, should be Rand, because that's the last section of the import path, but that's just a convention. They could, if they wanted to, change the name of the package to say random, and then all of the files in their source code would say package random. Now, again, it is possible to use a different package name, one that's not the same as the last section of the import path, but I highly discourage it. It is best practice to just use the convention and keep everything consistent. Now, one last thing to point out here is that in Go, packages live at the directory level rather than the file level. So if you're used to, say, Python or JavaScript, you might be used to importing code directly from other files. In Go, if all of the code lives within the same directory, then it's part of the same package, and you don't need to import and export code between files in the same package or in the same directory. So in Go, you would only need to import code if it lives in a different directory or a different package. And packages and directories are one and the same. You can't have multiple packages in the same directory. So the quiz question for this section is, what would be the conventional package name of a package with the path github.com/wagslane/parser? And the answer is going to be parser, because it should match the last section of the import path. The next question on the topic of package naming is, given the import path of path to rand, path/to/rand, which of these is a valid package name? So notice it's not asking which is a conventional, it's asking which one is actually valid. We've got random, rand, spam, any of these path. Well, rand would be the conventional name, but actually any of these could technically be used. Okay, it's time to write some Go code on our local machines, and you're going to need 3 things in order to make it through the rest of this chapter. The first thing is you're going to need an editor. I'll be using VS Code throughout the rest of this chapter to do all of our local development stuff. You can use VS Code, or you can use something else that you're more familiar with. If you do use VS Code, you'll probably want to install the official Golang plugin. The next thing you'll need is a Unix-like or SH-like terminal. So if you're on Mac or Linux, then the built-in terminal will work just fine. If you're on Windows, you have a few different options. Personally, I would recommend installing Ubuntu in WSL2. I'll link in the description down below how to do that, but you will need to have a terminal in order to follow along with these instructions. If you choose to use something like the default Windows command line, you're going to have to change some of the instructions in the terminal to kind of translate them to your own machine. The last thing you'll need is just to install the Go toolchain on your local machine, and I would recommend one of 2 different ways. The first is to use the official download page, and the second is to use the Webby download script. Either of them will work, and I've linked them both on this page, so you can go check them out and get Go downloaded. Now, once you've downloaded and installed Go, the way you can test to make sure that everything is working correctly is to type Go version in your terminal. If you get back a valid Go version, of at least version 1.20, which is what I'm using at the time of recording this video, then you should be good to go. Now, I need to point out at this point that some people get confused and think this is Go version 1.2. It's not. It's Go version 1.20, which is the same as Go version 1.20, which is one version greater than Go 1.19 or Go 1.19. So make sure that you're not on Go 1.2. That would be very, very old. If you're having trouble getting Go installed so that you can use it within your terminal, the first thing I'll have you do is definitely try closing your shell session and restarting it. A lot of times that can help just getting Go into your path. If that doesn't work, then Googling around can be one method to kind of try to figure out what's going on your machine. It's really hard for me to kind of predict what issues you might have, especially considering the fact that macOS, Windows, and Linux can all be a little different. But what I will recommend is that if you are having trouble, jump into the boot dev Discord and ask a specific question about the trouble you're having, and we'll be happy to help you out. So the question for this step, really just to confirm that we installed Go correctly and that we can use it, it asks, what does the Go version command print? And if we check the output, we can see it says Go version Go 1.20. So that's the version of the Go toolchain we have. Darwin, I'm on a Mac, so this is like the core Unix operating system. And then AMD 64, which is my CPU architecture. So it's going to be this bottom one. So we've talked about packages, and we've talked about how packages exist basically at the directory level in Go. Now we need to talk about modules. A module is a bigger idea than just a package. A module is kind of a releasable collection of Go packages. So sometimes it's just a single package, right? You have a single package, a single module, and you release it as one package. But other times you might break that main package up into sub packages, and you'd release all of those packages together as one Go module. Now, a repository is not a unique idea to Go, but it's sort of even greater than just a module. A repository, or a Git repository, is just a collection of code that you kind of keep in source control all at the same level, and it can contain one or more modules, though it's actually really common for a single repository to just have a single Go module within it. So while one monorepo can have many different Go modules inside of it, I would argue that's not usually the case. Typically, you'll have one Go module living in one repository. That's not a convention, that's just the way I've seen it more often than not. So for the sake of example, let's assume a Git repository that contains a single module. And that means that at the root of the Git repository, we'd have a single go.mod file that looks something like this. The first line contains the path prefix for the entire module. So remember, a module can contain multiple packages, and every package in that module, its import path is going to be prefixed with the path of the entire module. The next line just specifies the Go version, and the last line will specify any dependencies that this module depends on. So to answer the question, what is a Go module? An executable main package? No, that could be part of a Go module, but it's not a Go module itself. A collection of packages that are released together? That is accurate. A file of Go code? No, a module will contain many, many files of Go code. Or a library package. And again, no, not necessarily. You could have a module that's just a single library package, but a Go module can be many more packages than that, or it could be a main package, for example. So it's going to be a collection of packages that are released together. So we need to talk just a little bit more about these import paths. Now, if you're familiar with NPM from the JavaScript ecosystem, Cargo from the Rust ecosystem, or pip from the Python ecosystem, then you're probably familiar with the idea of a namespace for a third-party package. For example, I might make a package called leftpad, publish it up to NPM's central repository, and now anyone in the world just knowing my kind of namespace name, leftpad, can download and use my code as a dependency. The interesting thing about the Go ecosystem is that there is no central location for third-party packages like npmjs.com in JavaScript land. Instead, the Go toolchain sort of works on top of Git and actually uses the import path as the remote URL. And it looks to that import path for where it can go download code. So more often than not, you'll see modules with import paths that start with github.com or gitlab.com because that's where the code itself is hosted. An important exception to this rule that the import path is where you go to download the code is the standard library. You don't need to download standard library code. It comes packaged with the Go toolchain. So the question is, do packages in the standard library have a module path prefix? The answer is no. The next question is, what is an import path? And I know we've already talked about this, but I want to show you a more concrete example. So this is the github.com/wagslane/go-rabbitmq GitHub repository. So this is a GitHub repository that I maintain. It's just a little package for RabbitMQ users, a little Go client for RabbitMQ. So this is a library module and a library package. It's intended for other developers to actually import this code into their applications. It's not a standalone, main package. So let's take a look at the file structure. At the very root of the repository, we have the go.mod file. Now, this is that kind of simple standard setup where one Git repository happens to have one Go module or one sort of releasable unit of code. And if we take a peek inside, we can see that the go.mod file specifies the import path, github.com/wagslane/go-rabbitmq. So this matches the URL of the Git repository hosted on GitHub. Now, here's the interesting thing. This module only has one package that's exported to the outside world, and it exists here at this top level. So you can see all of these Go files, consume.go, consumeroptions.go, they exist at the top level of the repository. So when you import this package to use it, you just import from this root path because the root package is what you're importing. There are no sub packages to import here. But let's pretend for a second that we did want to export another package in the same Go module. So we have our top level Go module, go-rabbitmq, and the top level package that can be accessed at the same import path as the module. Let's say we added another directory. We could call it maybe networks, and inside it would be the networks package. If someone wanted to import that package, then they would take the import path for the entire module, github.com/wagslane/go-rabbitmq, which points to the root package, like we already talked about, and they would just append another /networks onto the end, right? So the module path serves as a prefix for any nested packages. So to answer the original question, what is an import path? Well, it's not an HTTP connection and it's not a RESTful server. It's a module path plus an optional package subdirectory. So we've talked about repositories, modules, packages, you've got Go installed. Now let's talk about how you can set up your local development environment. And some of this stuff isn't going to be necessary, and I'll point that out, but I do want to show you how I've set up my machine, and you can emulate the way I do it if you like that style. Now, I need to mention the Go path. If you're Googling around trying to figure out how to set up your local development environment for Go, you will almost certainly come across old, outdated articles that talk about the Go path. In kind of any version newer than, I think it's 1.13, right? So we're on 1.20 now. You can basically forget about the Go path. You don't need to worry about it. You used to have to put your code in the Go path. Now the recommended way is actually to not put your code in the Go path. It can be a little confusing, but again, generally speaking, you can just forget about the Go path, and if you find any articles that talk about it, they're probably outdated. The entire idea of Go modules is what replaced the old Go path. So the question is, do you need to put your code inside of your Go path? The answers are yes, it doesn't matter, and no, in fact, you shouldn't. And actually, in fact, you shouldn't. So I've altered my window layout so that it's a little bit easier for you to see what I'm doing. I've got the boot dev instructions over here on the left, and then I've got VS Code over here on the right with my terminal at the bottom. Cool. So I'm just here in my file system. I'm not within the Go path. I'm just kind of in my personal workspace, and we'll just follow these instructions. It says create a new directory and enter it. So we'll make directory hello go. And let me just ls, show you the new directory was created, and we'll enter that directory. Cool. Now, inside of that new hello go directory, I'm going to create a new Go module. So we'll do go mod init. And I keep all of my code on GitHub, so I'll do github.com/my username, because that's my namespace on GitHub, so wagslane, / the name of this project, which we're just calling hello go. Cool. It says go creating new module. Now if I ls, I should see that new go.mod file. Next, let's go ahead and take a look at that file. So you can see it just created a new module, github.com/wagslane/hello-go with the Go version, and there are no dependencies yet, so there's no other sections to the Go module file. So now that we're done with this step, the question is, why does Go include a remote URL in module paths, right? So this is a remote URL in theory, right? When we push this up to GitHub, we'll push it up to this URL. And the answers are to confuse new gophers, to ensure that developers are using source control, or to simplify remote downloading of packages. And it is definitely that last one. The next question on the same step asks, what is hello go in our case? The repository / directory name or the module path prefix. And in our case, it's actually the name of the repository. So again, if we were to push this up to GitHub, GitHub is the name of the website where it's hosted. Wags Lane is my namespace on GitHub, and hello go would be the name of the directory that we are in and the name of the repository up on GitHub. And then this next question is just to make sure that we completed the step properly. What does the first line of go.mod contain? And it contains module followed by the module path. Now, so that VS Code will work properly with all my syntax highlighting with the Go plugin, I'm actually going to reopen VS Code to that same directory, the hello go directory. So we'll just be working within this module for a second. And the instructions say inside of hello go, so now I'm inside of this hello go directory at kind of the top level of my VS Code window. It says create a new file called main.go. So let's go ahead and do that. Conventionally, the file in the main package that contains the main function is called main.go. Paste the following code into your file. Okay, cool. So we should all be familiar with this code by now, right? We've probably written code like this, I don't know, almost 100 times by now in the boot dev platform. Next, it looks like we're just going to run the code using the Go toolchains interpreter. So go run main.go. And we get a nice hello world printed to the console. There's sort of two main ways to run Go code locally. One is with the go run command, like we just used. The other is to use the go build command, which we'll get into in just a second. And actually, in general, I prefer the go build method. Go run is really only suitable for when you're running tiny little scripts like this one. And just to be clear about the difference, go run, so go run main.go, runs the Go code in the file that we pass in, right? In this case, main.go. And that's all it does. Go build actually builds a production executable, which is how you'll use your Go code in the real world. So I typically prefer building that production executable just because it more accurately reflects how your code will run in production. So the question on this step is, does go run build a production executable? And the answer is no. It just kind of one-off runs your code. It doesn't build any production-ready artifacts. Now, at the end of this same step, we're asked to execute the go help run command in our shell. So go help run, which just prints out a bunch of help information on how to use the go run command. And the question for the step says, which can go run accept as arguments? And if we scroll to the top, so here's where I ran go help run, we can see the usage information, and it says, run compiles and runs the named main Go package. Typically, the package is specified as a list of .go source files from a single directory, but it can also be an import path, file system path, or pattern matching a single known package. So which can go run accept as arguments, package names, file names. It actually looks like it can handle both. Great, now we get to use go build. So you can, for the most part, just forget about go run. You probably don't need to use it all too often. So go build compiles Go code into an executable program. So all you need to do is make sure that you're in the same kind of main package that you want to build. So I'm here in the hello Go directory. I can ls to prove it to you. We've got the main.go file here, package main, func main, all that good stuff. We'll run go build. We don't even need to pass in package or file names. It just builds the package of the current directory. So as you can see here, we have this new executable binary in our current hello Go directory. Now, if you remember way back to, I think, chapter 1 of this course, we talked about the difference between interpreted languages and compiled languages. And one of the amazing things about Go is that we build compiled executables that we can execute anywhere. So this hello Go binary, we can now copy this, put it on another machine, and run it without even needing to install the Go toolchain on that machine. This is compiled machine code. So we can now run this hello Go program like we would any other executable, /hello Go. And it prints hello world. Now, I do want to show you a little tip here, because every time you update your code, let's say I change this to Hello World 2, if I just rerun Hello Go, it still will just print Hello World, and that's because I didn't recompile my code. So a lot of new Go developers kind of forget to recompile their code, and they think they have bugs or their code's not doing what they expect. You have to recompile. What I'd recommend doing is just every time you update your code and want to rerun it, you should build and compile, and you can just do it in the same step by doing go build and then $& the name of your binary. So this basically says compile my code. If that succeeds, run the compiled binary. And the question for this step is, what was created after running go build? An executable file named main, an executable file named hello go, or a package named cmd? And in this case, it was an executable file named hello go, right? We've got it right there. It just kind of defaults to the name of the directory. The next question for this step is, what happens when you run /hello go? And I actually changed this to hello world 2. But if we do it again after changing the code back, the options are program panics, hello world is printed, or the code compiles. Hello world is printed. And it's important to understand here, the reason we don't say the code compiles is because at this step, /hello go, all we are doing is running the compiled binary. We're not recompiling the code. The next command in the Go toolchain that we're going to talk about is go install. Now, to be honest, I don't use it a ton, but I still think it's important to understand because you'll see it around. Okay, so ensure you're in your Hello Go repo, then run go install. So I'm here in the Hello Go directory, and we run go install. And next we navigate out of our project directory. So I'm going to go up one level. And what it's telling me is Go has installed the Hello Go program globally. So the Go toolchain, when we ran go install, basically compiled that code and then made it globally accessible to our entire machine. So now if I run Hello Go, notice without the / because I'm not running a program in my current directory, I'm running now a program that's in my path, it prints Hello World. So now I can use this script that I built anywhere on my machine, which is just super useful if you're building kind of scripts for your own local productivity. So the question for this step is, what does go install do? Saves local code to the remote source control provider, installs dependencies, or compiles and installs the program locally? And the answer is that it compiles and installs the program locally. Again, you would really only use this if you're building scripts for your own personal use on your machine. The next question for this same step is, code must be compiled with go build before running go install. It's true, false. Now, if you were paying attention, you probably noticed the answer here, but we actually ran go install without a binary existing in our current directory. So if I go back into the hello go directory and run go install, you'll see there's actually no hello go binary that exists here, and it works just the same. So the code does not need to be compiled with go build first. All right, so we've created a main package and a executable program. Now we're going to build a library package, a custom library package. So what we're supposed to do is create a sibling directory at the same level as the Hello Go directory. So I'm in the Hello Go directory currently. I'm going to go up one level, and let's see. So we've got Hello Go in here. I'm going to make a new directory called mystrings, and then we'll go into mystrings. And here we need to initialize a new Go module. So I'll do go mod init, github.com/wagslane/mystrings. And that module is created. Now to get my VS Code tooling all working properly, again, I'm going to just reopen VS Code to that level. So we'll go back and find the mystrings directory and open directly into that directory. Okay. Next, we create a new file called mystrings.go. So this is the go.mod that we created with the go mod init command. And now we're creating a new file called mystrings.go. And we want to paste the following code. Okay, so package mystrings, that's the first thing to notice, right? This is not a main package. So we won't be able to build this package as a standalone executable. This package will be kind of, the intention is for us to use it in our other Hello Go package. The other thing to notice about this code, aside from the package name, is that there is no main function here. Again, because it's not an executable program. We're just going to be exporting functions that can be used in our main package. Let's talk a little bit about this reverse function. So this is the only function in the mystrings package at the moment. And, theoretically, it reverses a string from left to right, although I haven't tested it. But the important thing is that we need to capitalize. We need to capitalize the first letter of the function's name. And that's because in Go, that's how we export a function. If it were little r, then this function would not be able to be used outside of this package. But we want to export it because we want to be able to use it in our main package, right, in the Hello Go directory, and kind of import this logic and use it. Now, we're told to run the go build command here in this directory, and you'll notice it doesn't actually seem to do anything. There was no executable file that was built because this is not a main package. But it is worth pointing out that go build is still a useful command because it checks for compile time errors. So for example, if I create an invalid token here and then run go build, we will get compile time errors. So it is still kind of useful just to make sure that this code compiles. So the question for this step is, what was the output of the go build command in the library package? Was it an executable program, or was the compiled package silently saved to the local build cache? Well, we didn't get an executable package, right? This is not a main package, so we don't get a nice runnable executable. Instead, it is silently saved to the local build cache so that it can be used later in an actual executable program. And then the next question is, why is the function capital R reverse instead of lowercase r reverse? And it's lowercase names aren't exported for external use, or conventionally uppercase names are used in Go. The answer is that lowercase names are not exported. So by convention, functions can have either a lowercase name or an uppercase name, and uppercase names are exported from the package. So this next question is, does a package in a folder named date parser need to also be called date parser, right? Does the package need to be date parser? Now you'll notice that we created a directory called mystrings and a package called mystrings. And if you remember back to earlier in this chapter, we talked about how by convention, that's the best way to do it. It's not necessary, but it is the convention. Okay, so now let's use our reverse function back in the main package in the Hello Go directory, right? So it says modify Hello Go's main.go. So I need to reopen, I'm going to open VS Code back into the Hello Go directory. It says modify Hello Go's main.go file. Okay, so we'll use parentheses here so that we can do some multiple imports. And we'll be using the import path that matches the module name of our mystrings package. So in my case, it was github.com/wagslane/mystrings. And then here we just copy this code from the instructions. And in fact, let me space this out so we can see it just a little bit better. Okay, cool. So we've imported the mystrings package, and then down in our code, we can use mystrings, which is the name of the package, .reverse to call that exported function. Okay. Now, because we've added a dependency, we need to update our go.mod file. So edit the Hello Go's go.mod file to contain the following. This is the important part down here. So we need to add replace example.com username mystrings with ... mystrings, and require example.com/username/ mystrings version 0. Now I do need to update this, right? Because I didn't use example.com. I used github.com/wagslane. Now what's going on here? Right? Go's dependency management is very heavily based on Git and remote URLs. So normally what you would do is take your mystrings package and push it up to GitHub and then import it from there. And sort of all of the Go packages in the world that require the mystrings package will point up to that remote location, that remote server. What we are doing here with this replace and require, well, specifically the replace, is we're kind of doing a little hack to get things to work locally without having to publish to Git. So we're basically saying, I want you to take this string, this import path, right? github.com/wagslane/mystrings, and don't go look for it out on the internet. Instead, just resolve it to this path, /mystrings, right? And now because, well, I should probably get back into the hello go directory, right? /mystrings, this is the directory containing the mystrings package, right? So we're basically just saying, replace this with my local file system. We're telling Go how to find this package on our machine. So now that we've made those changes, we can build and run this program again. So go build /hello go, build and run, and it looks like it's working correctly. This function is supposed to reverse the string, and we get this nasty little ole. And the question is just asking us what was printed, and that's what we got. On the same step, this next question asks, how does the Go toolchain know where to find the imported code? NPM hosts the files publicly, it downloads it from Google's servers. We used the replace keyword in the go.mod to point it to the relative location of mystrings, or it was fetched from GitHub. Now, again, I want to point out that most of the time you'll be fetching code from GitHub or GitLab or some remote source when you're using third-party dependencies. In our case, we used this replace keyword to point the Go toolchain to the location of the mystrings package on our machine. So we already briefly talked about this, but I just want to reiterate that this little replace hack is useful for kind of testing and doing things on our local machine, but it's not suitable for production. Generally, what you would do is push up that mystrings Git repository to GitHub and then import from there. So you will typically not see replace aliases in production go.mod files very often. You'll just see packages sort of required vanilla from their remote location. So now we're going to practice using a remote third-party module. It says create a new directory in the same parent directory as hello go and mystrings called date test. So let's go back up one level and create a new directory, make dir date test. And then I'm going to go ahead and again reopen VS Code into that directory. Okay, create a main.go with this code. We can do that. Next, initialize a module. So we do go mod init. And again, I'll just use github.com/wagslane/date test. Creating new go.mod. To add module requirements and subs, do go mod tidy. Okay, cool. I'm going to ignore that for just a second, and instead I'm going to follow the instructions. It says download and install the remote Go TinyDate package using go get. Okay, so we've used go install in the past, right? Go install installs an executable on our machine to be used anywhere. Go get is how we go download and install third-party dependencies. So we're going and grabbing the github.com/wagslane/go tinytime module. And it gets added automatically to our go.mod. You'll see that, and it just kind of grabs the latest version. Cool. Print the contents of your go.mod. I don't need to run that because we've got it open here in VS Code. And then compile and run our program again. So let's do that. Go build and run, and it's going to compile to a file called date test, right? Because that's the name of our directory. Cool. And as you can see, it's printing out this date here. So what did we do, right? We used go get to download code from this remote location, which also happens to be the import path, right? Because that's how Go packages work typically. So let me go grab that and just show you, this is a package that's hosted on GitHub. So the Go toolchain actually went to GitHub and downloaded this code, right? Added it to the go.mod as a dependency, and then created this new file called go.sum that kind of contains any transient dependencies or dependencies used by the Go TinyTime package that we just imported. So it kind of keeps track of everything that we're using. And the question for this one is, how did the Go toolchain know where to download the Go TinyTime package? Oh man, this question is not optimized for this ridiculously zoomed in view. It says the module import path is used for remote lookups, e.g. github.com/wagslane/go-timingtime. Or the Go toolchain has every open source Go module's location memorized. That is not true. It just does a remote lookup, right? It goes and fetches that from the remote Git URL. And then just to make sure that we did the step correctly, it's asking us what was printed after running the new date test program. You can see it right there. And it looks like it's this 2020-04-03, right? It's this hard-coded date in RFC 3339 format. So hopefully that last section gave you a taste of local development, at least showing you how to build and compile some code on your own machine. We'll obviously be doing a lot more local development at the end of this video with the project, but for now, for the rest of this course, we'll be back working in the boot dev web interface. Cool, so we're on to talking about clean packages. And this is kind of just an article that I'm not going to bother reading out loud on screen, but I'll talk about each individual section as the questions are asked. So the question is, should you export code from the main package? And that's talked about down here. It's basically simple. Don't export code from the main package. And if you think about it, it makes sense. There's no reason to capitalize function names in the main package because no other packages can import from a main package. A main package is built into its own standalone executable. It's not a library. So capitalizing functions in the main package is just kind of confusing because it kind of signals to developers that you're writing code that's meant to be imported and it's not. This next question says, when should you not export a function, variable, or type? Now, this is an interesting question. I think a lot of newer developers think, well, maybe I should just export more stuff because maybe the users of my package will find it useful. You actually want to think in the reverse. You want to export as few things as possible when you're building library packages, because anytime you export a function, you now need to support that function, right? You can't really take it away later. Everyone's code will break, right? So you should really think about what you're exposing to your users as like the surface area of a shape, and you want to keep that surface area as small as possible to keep the maintenance burden down and to make your package easy to use, right? The fewer things that your users need to know about in order to effectively use your package, the easier it'll be to use. So when should you not export a function, variable, or type? When the end user doesn't need to know about it. Hide everything that they don't need to know about. The next question is, should you often change a package's exported API? So API stands for Application Programming Interface, and basically anytime you export something from a library package, you're adding that thing to the package's API, right? It's the interface that other developers will use to access your package. So should you often change a package's exported API? The answer is that no, you should try to keep changes to your internal functionality, right? Imagine if the Go programming language, let's say the standard library, changed fmt.println to fmt.print, right? And just removed fmt.println. That would break an immense amount of code, right? So you don't want to go about publishing packages that you intend to kind of update the API for very rapidly. Stable APIs are good APIs. So should you often change a package's exported API? No, try to keep the changes to internal functionality. Yes, move fast and break things. Or if the package is main, then yes. The answer is just no, try to keep changes to internal functionality. Again, if the package is main, then it's irrelevant because you're not building a library. I want to talk about the difference between concurrent or parallel programming and synchronous or sequential programming. Now, it's worth pointing out at this point that concurrency and parallelism are different, and we'll talk about their differences in a future course. For now, we're going to kind of treat them as the same idea, and I'll just kind of refer to them as concurrency. Similarly, sequential programming and synchronous, they're slightly different terms, but I'm going to kind of bucket them for the purpose of this discussion. We'll be really comparing concurrent code to synchronous or sequential code. So let's start with the easy one. Let's talk about synchronous or sequential programming. Say we have some code, x : = 5, x++, and then maybe fmt.print line x. The nice thing about this code, and what makes it synchronous or sequential, is that the code executes in order from top to bottom, right? First, we create a variable named x set equal to 5, then we increment it by 1, and then we print x, right? Everything's happening in order from top to bottom, one thing at a time. Now, this is usually what you want. It's simple, it's easy to reason about, it's easy to write code this way. The problem is sometimes it's not the most efficient way to write performant code, or code that can run as fast as possible on a given set of hardware. So in order to understand how we can maybe optimize this, we need to look into how your computer's CPU, or central processing unit, works. So your CPU has a clock speed, which basically, like from a very high level, means how many instructions it can do per, let's say, second. Those aren't necessarily the units, but it is basically how many computations it can do per amount of time. We could just say it's seconds to keep things simple. Okay, so when we're analyzing this code over here on the right, basically what needs to happen is first we set x equal to 5, and that takes up one instruction, right? After that, we get to increment x by 6, that'll take up another instruction, and then we get to print x. So the speed at which we can execute this little program here is dependent on how fast the CPU's clock speed is. So if we want our program to go faster, we can basically do one of two things. Either we can reduce the number of instructions required for our program to execute, or we can get a faster CPU, one that can do more instructions per second. The problem is getting a faster CPU sometimes is really, really expensive. And so instead of getting a faster CPU, what we've kind of done over the years is instead add more CPUs. And in this case, we've kind of broken the CPU up actually into what we call different cores. So you might actually have a quad core processor, each of which, let's say, does, 5,000 instructions per nanosecond. I'm totally making these units up, but you get the idea. Any one of these CPU cores can only do 5,000, but the interesting thing is they can all do 5,000 per nanosecond at the same time. So if we distribute our program across all of the cores, in theory, we should be able to go about 4 times as fast. Again, if we use all 4 cores instead of just one. The problem is that most code we write can't take advantage of all 4 cores. For example, let's look at this code over here. We set x equal to 5, and then we increment it, and then we print it. It has to happen in 1, 2, 3, right? In order 1, 2, 3. We can't do all of these instructions at the same time. If we did, then x++ would have nothing to increment because we never would have set an x variable equal to 5 in the first place, and print line x would have nothing to print because x hasn't been set yet. So writing concurrent or parallel code can drastically speed up the performance of our programs because we're able to distribute kind of all the instructions that we need to compute across multiple cores. The problem is we do actually need to write our code in a different way. We need to expect that some of the instructions are going to happen at the same time, and that's what's going to speed up our program. So let's say we had a little bit more code in our program here. Maybe we have y : = 6, y minus fmt dot print line y. Okay, this code here in this block kind of dependent on each other, right? We have to do it in 1, 2, 3 order. And the same goes for this block here. But we don't have to necessarily do this block of code where we calculate and print x before or after we calculate and print y. They're kind of separate in that way. So what we can actually do is take this block of code and execute it in one core, and at the same time execute this other block of code in another core, doing them at the same time. So let's sort of visualize the runtime of this program here. If we run this code synchronously or sequentially, right, not taking advantage of 2 CPU cores, but instead doing it all on one core, then our running time might look something like this. I don't know, let's just say 6 nanoseconds. But instead, if we run it across 2 cores in parallel, each core executes at the same time, and they'll each take approximately, let's say, 3 nanoseconds. So we're done in half the time, again, because we took advantage of the hardware that was available to us. So to wrap up, writing concurrent code in many cases can drastically reduce kind of how long it takes to run our programs. And it depends just a little bit on kind of fundamentally what we are trying to do. So in this case, we literally could take a program and chop its runtime in half by utilizing a little bit more hardware. So this chapter is going to be all about concurrency in the Go programming language. And the great thing about Go is how easy it makes it to write concurrent code. So the question is, how do we write concurrent code in Go? What's the syntax? Well, there's actually a really awesome built-in keyword to the Go programming language, the Go keyword, and it spawns a new Go routine when you use it. Now, a Go routine is kind of unique to the Go programming language, but at a high level, you can just think of it as a separate thread of execution. We're essentially telling the Go programming language, hey, all this stuff in this function, right, that I'm calling with the Go keyword, can happen in parallel, right? We can go execute that on another core of the CPU if we need to. So whenever we use the Go keyword, execution kind of immediately jumps to the next step after the function call, right? So this do something function will kind of go be executed in parallel, right? And then execution continues in the current function, kind of just on the next line. And then as a last note, before we jump into some code to see how this really works, when we use the Go keyword, we're not able to capture any return values from this function call, which makes sense, right? Because we're kind of moving on. We can't wait for the function to finish and return some stuff. That's the whole point. We want the function to go kind of do its thing on another thread. So let's try this out in an assignment. It says, at Melio, we send a lot of network requests, right? Requests over the internet. Each email we send must go out over the internet. To serve our millions of customers, we need a single Go program to be capable of sending thousands of emails at once, right? So we need to be able to do lots of things at once. This is what Go routines allow us to do. Edit the send email function to execute its anonymous function concurrently so that the received message prints after the sent message. So let's go ahead and run the code in its current state. And we get email received, hello there, Stacy. Email sent, hello there, Stacy. Right, so it looks out of order. Now here's our send email function. It takes a message as a string parameter. And the interesting thing is it calls this anonymous function here, right? So it's defining this function and then immediately calling it, where it's going to wait for 250 milliseconds and then print email received. And then this function will exit and it will print email sent, right? And then print the message. So again, that's why this is out of order, right? We're executing this function first, and then we're moving on to the next line. So the way we fix this is by using the Go keyword to execute this bit of code at the same time as this bit of code, right? The Go keyword will immediately move down to line 13 on the main thread or the main Go routine and spawn a new Go routine to kind of do this in the background. And because of this waiting time, the email received message should happen afterwards. So let's go ahead and run this again. Sent received, looks good to me. So you may have been thinking to yourself, well, how useful is it to call a function in a Go routine if I can't even get the return values? The answer in Go is that we use channels typically to kind of resynchronize our code. So typically we'll use Go routines, or the Go keyword plus some function, to go do a bunch of computation all at the same time. And then we can kind of resynchronize either in the main Go routine or in some other Go routine by passing data back and forth between Go routines using channels. A channel is really just a thread safe or Go routine safe queue. We can put stuff in one end and read it out the other end in the same order. So we'll typically have one or more Go routines kind of sending data into the channel. Maybe they finished a calculation, they're returning their results over the channel, and then we'll have one or more Go routines on the other end reading that data off of the channel and processing it in some way, maybe sending a report, maybe printing it to the console. So this is the syntax for making a channel, and channels are typed. So we can say this is a channel of integers. And then we can send data into the channel using this arrow operator. It's really pretty intuitive. We're saying 69 is being sent into the channel. And then it's actually the same operator to read a value out of a channel. We just move it over to the other side. Again, super intuitive. We're reading a value out of the channel and saving it into the variable v in this example. Now, it's important to understand that both of these operations, sending and receiving on a channel, are blocking operations. So if I'm trying to send a value into a channel and there's no other Go routine on the other side that will be able to read it out, then my code will actually stop and wait on this Go routine until there is a reader ready. And the same goes for reading. When a Go routine gets to this section of code, if there's nothing being sent into the channel on another Go routine, then this code will just sit and wait until something is sent. So let's move on to the assignment. It says run the program. You'll see that it deadlocks and never exits. So a deadlock is basically when all of the Go routines in a program are blocking and there's nothing for them to do. It means there's a bug in the code. So let's run the code just to see what that feels like. Although I think it's just going to feel like it's running the code for a long time. So I'm going to go ahead and cancel that. The filter old emails function is trying to send on a channel and there's no other Go routine running that can accept the value from the channel. Okay, so let's take a look. Filter old emails takes some emails as an input, creates an is old channel, and then it looks like it loops over the emails, and if they are before a certain date, it's going to pass the Boolean true into the channel, otherwise it's going to pass in false. And then once that loop exits, it's going to read out of the channel here and print to the console, whether or not the emails were old. Okay, cool. So this makes sense. This makes sense why this is blocking, right? This first send, either here or here, whichever one happens first, is going to block because the reader, like that code hasn't happened yet. This is the same Go routine, right? This is not happening at the same time as this is happening. So we'll use a Go routine to fix it. Fix the deadlock by spawning an anonymous Go routine to write to the is old channel instead of using the same Go routine that's reading from it. Okay, cool. So we need to run this loop essentially in a new Go routine. So we'll do go func, and we'll just use an anonymous function here because we don't really care about naming it. And we'll just run that entire block of code in a new anonymous function. So now this and this will happen at the same time. Let's go ahead and run that. Cool, and this looks like what I would expect. I'll go ahead and submit that. So there's this concept of a token when we were talking about concurrent programs. A token is basically a unary value, right? So not binary, there's not two possible values, true and false. Unary, there's just one possible value. And when there's just one possible value, we really don't care much about that value. It's not interesting in any way, right? So it's not that we care what is passed when we're working with tokens, it's that we care when and if something is passed through a channel at all. So for example, this code here is reading a value out of this channel, and it's just discarding whatever it reads out. It doesn't even care what it is. It's just waiting to see kind of when something comes through the channel. So let's move on to the assignment and kind of put that into practice. It says our Mailio server isn't able to boot up until it receives the signal that all of its databases are online. And it learns about them being online by waiting for tokens, which are just empty structs, on a channel. Complete the wait for DBs function. It should block until it receives numDBs, so this integer here, tokens on the dbchan channel, right? So this is a channel of empty structs. And again, empty structs are tokens. They're unary values. They're not interesting. They don't have any fields. Each time it reads a token, the get databases channel Go routine will print a message to the console for you. Okay, so I'm guessing that's down here. Yeah, it looks like it's going to watch and print here. Okay, so let's get started and write some code. It should block until it receives numDB's tokens. So it's a variable amount of tokens. So I guess the easiest way to do this would be with a loop. So for I = 0, I is less than numDBs, I++. And then in here, we're just going to wait for a token to come across the DB channel, right? So it'll block once, and then it'll move on to the next iteration of the loop, block again, move on until we've waited for, numDB's tokens. And then block until it receives the tokens. Each time it reads a token. That's it. Looks like we don't have to return anything. So let's run that. Database 1 is online, 2 is online. This looks good to me. So now let's talk about buffered channels. So the channels we've been using up until this point haven't really stored anything in them, right? We needed a sender and a receiver at the same time. As soon as the sender sends, the receiver receives. There's nothing kind of stored in the channel at any given time. But that is exactly what a buffered channel is. So we have a buffer of some length, let's say 5 different items, and senders can actually send into the channel even when there's no receivers until the buffer fills up. So a sender could send 5 things into the channel, and then the buffer is full, the channel is full, right? And when a receiver finally goes to read and pop items off of the other end, it will read and pop them off in order, one by one, until the channel is empty. So this is the syntax we'd use if we want to make a channel of integers with a buffer size of 100. We just use that optional second parameter to the built-in make function. So let's move on to the assignment. It says we want to be able to send emails in batches. A writing Go routine will take an entire batch of email messages to a buffer channel. We'll write an entire batch of email messages to a buffer channel. And later, once the channel is full, a reading Go routine will go read all of those messages. So we can actually go find where that's happening here in the test suite. Okay, here. So send emails. Oh, nope, this is where they're getting read. I'm sorry. I'm silly. The function that we'll be working on is what's writing into the channel. So emails to send is the channel. We're supposed to write an entire batch of emails into the channel, and then theoretically, sometime in the future, those emails will be read out of the channel and actually sent off. Okay, cool. So what happens if I run the code in its current state? I'm kind of imagining that it's going to block forever. Yeah, that's never going to exit. So add emails to queue is getting called here, and send emails is getting called here. And notice that they're getting called on the same, they're both running in the same Go routine, right? Add emails to queue there's no Go keyword anywhere that I see. So that's why we are blocking here. There's no reader on the other end, right? But because we want to do this batching, we actually should be able to do it all in the same thread. We just need a big enough batch size. So we need a buffer. If we buffered this emails to send channel with the length of the emails slice, then we should have enough room to push all of the emails into the buffer channel. Let's go ahead and try that. Cool, that looks like it is working. Channels in Go can actually be closed. And there's really only one reason you'd want to close a Go channel, and it's to indicate that you're done with it. A channel should always be closed from the sending side. So the sending Go routine, the one that's pushing values into the channel, will be the one to close the channel. And that will indicate to any readers of the channel that this channel is closed. There's nothing else to read from it. And the actual syntax is really simple. It's just the built-in close function where we pass in the channel itself. Now, on the reading side, we can actually check if a channel is closed using this kind of optional second variable that comes back when reading a channel, this OK variable. It's a Boolean. If the Boolean is true, the channel is open. If it is false, the channel is closed. If the channel happens to be buffered, then OK will remain true until the channel is emptied out. So OK will only be false once the buffered channel is empty and closed. The last thing I'll mention before we jump into the assignment is that you never want to send a value across a closed channel. If you do, that Go routine will panic. And that's why it's really important that you only ever close a channel from the sending side, because that Go routine is going to be the one that knows when it's done sending values. Okay, on to the assignment. It says, Emilio, we're all about tracking what our systems are up to with great logging and telemetry. The send reports function sends out a batch of reports to our clients and reports back how many were sent across the channel. It closes the channel when it's done. Okay, so the send reports function here sends the reports, or sends the number of reports across the channel and closes the channel. Great. Complete the count reports function. It should use an infinite for loop to read from the channel. If the channel is closed, break out of the loop. Otherwise, keep a running total of the number of reports sent and return the total number of responses. Okay, cool. So first things first, we need to keep track of a total. So let's start it at 0. And we know that at the end of the function, we'll be returning the total, right? Then it says use an infinite for loop to read from the channel. Okay, so for. And then we need to read from the channel. So we'll do numsent and read from the numsent channel. Okay, if the channel is closed, break out of the loop. Ah, right. So we need to use that syntax to check if the channel is closed. So if not okay, if the channel is closed, then we'll return total. Or I suppose we're returning down here, so we could just break. Let's just do that instead. Break. Otherwise, we do total plus equals numsent. And it's important to understand that as soon as OK is false, numsent will just be a 0 value. So it's not a valid value that was sent across the channel. So it's safe to just break like that. Okay, cool. This is looking correct to me. Let's go ahead and run that. Let's see. Batch of 15, 38, and 61 sent. Do those add up to 114? Looks like they might. Like my terrible in my head arithmetic says that that's perfect. So I'm going to go ahead and submit it. The range keyword works with channels as well as slices and maps. So we can actually range over the channel and it will block until a value is ready. It will read it into, in this case, the variable item, and then execute the body. And it will do that over and over and over for each new value coming across the channel. And will only exit the loop once the channel is closed. So onto the assignment. It says, it's that time again. Melio is hiring and we've been assigned to do the interviews. For some reason, the Fibonacci sequence is Melio's interview problem of choice. We've been tasked with building a small toy program that we can use in the interview. Okay, so complete the concurrent Fibonacci function. If you're not familiar with the Fibonacci sequence, I don't want to go like too crazy far into it, but it's basically this sequence of numbers here where each number is the sum of the two preceding numbers. So 1 and 2 equal 3, 2 and 3 equal 5. In fact, you probably can't even see that. Let me zoom this in a little bit. So 1 and 1, or 1 and 2 equal 3, 2 and 3 equal 5, 3 and 5 equal 8, right? So it's just this kind of set sequence of numbers. Okay, complete the concurrent fib function. It should create a new channel of ints. So let's go ahead and do that. So channel ints, make channel of ints. Great. Call Fibonacci in a Go routine, passing to it the channel and the number of Fibonacci numbers to generate. Okay, so we have a Fibonacci function here, and it takes the numbers and the channel itself. So let's start a Go routine in an anonymous function. Go func, call the function, and In here, we call Fibonacci. Let me just copy and paste that because I can't spell it. It takes n and this channel of ints as input. Okay. And then use a range loop to read from the channel and print out the numbers one by one, each on a new line. Okay, so the Fibonacci function is going to pass its results back over this channel. So it's taking the channel and it's going to act as the sender on the channel. So we down here below kind of where we're spawning that go routine need to act as the reader. So for v in range channel events, print out the numbers one by one. Print line v. And then when the Fibonacci function is done, it will close the channel, so we'll exit from the loop. Cool. Let's go ahead and run that. Does this look accurate? 10 numbers. 0 and 1. 0 plus 1 is 1. 1 plus 2 is 3. 2 plus 3 is 5. Looking good to me. On to select statements. So a select statement is similar to a switch statement. If you're familiar with switch statements from other languages or from Go, where it's kind of this if-else chain, and we're really looking to kind of match a specific case. But what's interesting about select statements is they're unique to channels, and they basically let us listen on two different channels and kind of execute one block of code, or rather execute a block of code for the channel that sends a value the soonest. So we can kind of simultaneously listen on both channels, and if this channel sends a value first, then we'll do, one thing. Otherwise, when this one sends something, we'll do another thing. So one Go routine can kind of process events from multiple channels at the same time using a select statement. So this is the syntax here. We create a select block and then multiple cases, one for each channel that we are interested in kind of listening for values on or reading values off of. So if this channel ints has a value ready, then this case will be executed. Otherwise, if this one, if channel strings has a value ready, then this case will be executed. If both have a value ready at the same time, then one will be chosen randomly. So you don't want to kind of be dependent on any weird ordering. Basically, as stuff comes across, it's going to get processed. So on to the assignment. It says, complete the log messages function. Use an infinite for loop and a select statement to log the emails and SMS messages as they come across the two channels. Okay, so channel of emails, channel of SMS messages. Add a condition to return from the function when one of the two channels closes, whichever is first. Use the log SMS and log email functions to log the messages. Okay, cool. So infinite for loop, start there. And inside we'll need to select. Can use this as our syntax guide over here. We've got case, email, okay. Value from channel of emails. If that case fires, then we say if not, okay. So if the channel is closed, we just return, and this function returns nothing. So we could just naked return. Otherwise, we need to log email. I think that's, yeah, log email. There it is. The email. Cool. Other case, SMS, okay, from the channel of SMS. If not okay, return. Otherwise, log the SMS. Right? So this for loop will just go forever until one of these two channels closes, in which case it'll return. Right? And it's important that we return before we do the logging, because when a channel closes, the OK variable is false, and a 0 value comes across the channel that wasn't sent into the channel, if that makes sense. So like the closure happens after the last value comes out. Let's go ahead and run that. Looking good to me. We'll submit it. The select statement also has a default case. You don't always need to use the default case, and basically the default case only fires if you're interested in non-blocking. So, for example, this select block here will fire the case that kind of pulls this V value out of this channel if there is a value ready to be pulled at the time that we enter the select block. If there's not a value ready to be read out of the channel, then the default case is fired immediately. So it kind of turns the select block into a non-blocking block of code. And then there's a few things we're going to need to know for this assignment. The first are these there's several standard library functions. So time.tick returns a channel that sends a value on a given interval. So we could say pass in a second to time.tick, and we would get back a channel that receives a value once per second. Pretty cool for like rate limiting, doing something on a set interval. Time.after sends a single value after the specified time has passed. So if we created a new channel with time.after and passed in 1 second, then one value would come across after a second had passed, and then the channel would be closed. Time.sleep just blocks for the specified amount of time. In fact, I think we've kind of seen it around so far in the course. And then we have read-only and write-only channels, and these are pretty cool from like a type safety standpoint. Basically, we can take a channel and we can pass it into a function, but specify that within the function, we are just going to read from it. So then within the function, the compiler will not allow us to write to it. So this is a great way to kind of keep Go routines safe in terms of which functions are readers of channels and which functions are writers of channels. And we can do the same thing with writers by using this syntax here. So readers read out of the channel, writers write into the channel. The assignment says, like all good backend engineers, we frequently save backup snapshots of the Malio database. Complete the save backups function. Okay, it should read values from the snapshot ticker and save after channels simultaneously. Okay, so the ticker and the save after, these are channels that are created down here using those standard library functions that we just talked about. Okay, so we need to use a select statement, it looks like. Should read values continuously. So I'm gonna use a for loop and a select statement. If a value is received from snapshot ticker, call take snapshot. Okay, so case, val, okay. We want to read out of a snapshot ticker. Do we care about the channel being closed? Let's see. Values even saved after. No, actually we don't. So we just need the value from snapshot ticker. Oh, and we don't even care about what the value is. So we can just completely ignore the value. Call take snapshot. Okay. If the value is from saved after, so case save after. Call save snapshot and return from the function because we're done. Okay. So again, we don't need to return anything from this function. Doesn't have any return values. If neither channel has a value ready, call wait for data. Okay, so default wait for data. And then sleep for 500 milliseconds. So time.sleep, time.millisecond times 500. Okay. This is looking good. So we've got this infinite for loop. We're looking for values that are coming across these channels. Anytime a snapshot should be taken, we take it. Anytime this save after channel passes us a value, we will save the snapshot and exit the function. Otherwise, we'll wait for data, whatever that does, and sleep for 500 milliseconds. In fact, I'm curious, what does wait for data do? Okay, so all these do is kind of print different messages. So let's go ahead and run that. Okay, cool. So nothing to do waiting, right? So every 500 milliseconds, we're kind of logging out that we're waiting for things to do, taking backups, and finally saving the backups at the end. Cool, let's submit this. This looks correct to me. Dave Cheney is a fantastic author and contributor to the Go programming language and the Go ecosystem. And he has this awesome article that I would definitely recommend checking out. It's called Channel Axioms. I've kind of summarized it here, and we're going to talk about a few key points. So the first is that ascend to a nil channel blocks forever. So the zero value for a channel is nil. If you don't use the make function to initialize a channel, then the channel's value is just nil. And if you try to send on a nil channel, your code's just going to block forever. Similarly, a receive from a nil channel will just block forever. Now, this one's a lot more dangerous. Trying to send on a closed channel panics. So you need to be really careful and make sure you're only closing channels from the Go routine or the function that's writing to the channel so that you can be sure you'll never try to write to that closed channel again. And then a receive from a closed channel returns the zero value immediately. So if you're trying to pull data out of a channel and it's already closed, you'll just get the zero value. And we've already seen how you can also kind of optionally check for that OK value, which will be returned as false. So what happens when you read from a nil channel? The receiver will block forever. And what happens when you send to a closed channel? You'll get a panic, and you never really want to panic in Go. That's almost always indicative of a bug. So channels are one tool that we have in Go to sort of synchronize state across different Go routines, right? We can send data from one Go routine to another safely. Mutexes are another built-in primitive. Well, rather, they're not built into the language, but they're built into the standard library. And they allow us to also sort of communicate or share data between two Go routines. Mutexes work by locking access to protected resources so that only one Go routine can access that resource at a time. So the sync.mutex type is exposed by the standard library. And basically the way it works is you create a new mutex and then you share it across many different Go routines. And then you wrap whatever code that is dangerous or whatever resource that is dangerous that you never want two Go routines at the same time kind of getting access to, you wrap them in a call to lock and unlock. So for example, in this function, we have this protected function. And it calls mutex.lock at the top of the function, and then it defers an unlock. And what this means is when one Go routine calls this protected function, if it's the first call to this protected function, then this mux.lock will lock the mutex for this Go routine, and it will be able to move on and kind of complete the rest of the function and then call mutex.unlock. Every other Go routine that calls this function, right, on this shared mutex, will actually block at the mux.lock function call because the mutex is locked by another Go routine. So mutex stands for mutual exclusion because it excludes every Go routine except for the one that holds the lock. And once that first one actually unlocks the mutex, then one other Go routine is able to pick up the lock, execute its protected code, and move on from there. So it's a way to take some dangerous resource and sort of share it across many different Go routines safely. There are a couple of different reasons why you would want to protect a resource and only allow a single Go routine to kind of work on that resource at a time. But one super common one is maps. So maps are not thread safe in Go. If two different Go routines are trying to read from and write to the same map, Go will actually panic because that has a very high likelihood of causing a race condition. And if you're wondering what a race condition is kind of what it sounds like. It's when two different Go routines are effectively racing to get access to a specific resource. So imagine a case where we have a count variable and it's set equal to maybe 5. And you have one Go routine that reads that count variable and saves it into, say, another variable, my count, right? And then maybe doubles it and then saves the doubled value back into count. Well, what if we have another thread of execution doing the same thing? If they both read count, let's say they both read 5, double 5, so now they both store 25, and they both go to write 25 back into the variable, all you did was double 5 once, where you were probably expecting to have two different threads doubling the variable. So you probably were expecting for it to go 5 to 25 and then double again, 25 squared, 625, I think. The point is, depending on exactly how those operations are threaded into the CPU, you'll actually get different behavior. So race conditions are awful to debug, and mutexes allow us to lock access to those protected variables. So we could wrap that count variable in a mutex to avoid it being accessed at the same time by different Go routines. So this should make a lot more sense once we write some code. The assignment says we send emails across many different Go routines at Mailio. To keep track of how many we've sent to a given email address, we use an in-memory map. Okay, so we've got this counts map stored within a safe counter struct. The map is of string to integer. And then we've got a pointer to a mutex that we're sharing across all of these different Go routines. Our safe counter struct is unsafe. Update the increment and the value methods so that they utilize the safe counter's mutex to ensure that the map is not accessed by multiple Go routines at the same time. Okay, so we've got the safe counter, and it looks like it's going to be kind of copied across different Go routines. So we create one instance of the safe counter. It's getting passed into this test function. And then we've got this Go routine. It looks like we're spawning Go routines in a for loop and then using that safe counter, right? So increment is being called many different times across many different threads of execution. And that is not safe. Cool. So let's see what happens if I run the code right now. Jill has 3 emails. John has 4. And if I look down into the tests, like that is wildly inaccurate, right? So it kind of looks like what's happening is like the example I described where maybe you're multiplying numbers together at the same time. So you kind of end up with a smaller number because everyone's doing it at the same time and then saving the variable back. It kind of looks like that's what's happening. We're getting these tiny results because all of these different Go routines are incrementing the number at the same time. Okay. So we need to lock this down. sc.mux.lock. So lock the mutex and then defer the unlock. It's important to understand that we could do this and it would be the same. Right? We lock, we do the dangerous thing, and then we unlock. But this is the preferred way, kind of the idiomatic Go way to do it. It's just a little safer, right? If we add multiple returns, the defer will never not execute. So that's how we're going to do it. And then we also need to lock on the val function because reading and writing at the same time is also dangerous. Cool, let's run that. See if we get some bigger numbers in our counts. Notice it's taking a lot longer to run. And that's because we're locking and unlocking. So every thread has to kind of go one after the other. So it slows it down, but it's a lot safer. So we get these accurate counts. Let's go ahead and submit that. So as we discussed, a mutex is called a mutex because it's short for mutual exclusion. And the conventional name for a mutex is mutex, or sometimes it's abbreviated to mux. Personally, I use mux a lot. So to answer the question, what does it refer to? It's going to be mutual exclusion. The next question is how many threads or Go routines can lock a mutex at once or at the same time? The answer is 1, right? If any more could lock it at the same time, it wouldn't be very useful. The next question is, why would you use a mutex? To safely access a data structure concurrently, to stop other packages from using my code, to protect data from network access, or to encapsulate private data members of a struct. It's going to be to safely access data concurrently. Time to talk about another type of mutex. So we've already covered pretty much all of the functionality you need to know about the sync.mutex type, but there's another type. There is a sync.rw mutex or sync.read-write